In the last video, we took a look at Lenz's law, and now we're finally in a position to state Faraday's law of induction. So if you remember 2 videos ago, I drew this diagram where I showed a region where the magnetic field strength was increasing, and we saw that the induced electric field lines were circles that just plain closed in on themselves and were oriented counterclockwise. Now let's imagine that you have a wire loop here somewhere. This electric field line here would follow that loop, which means it would shove charges around and do work on it. And in a later video, we'll go ahead and state that more explicitly. But the thing is it'll always be pushing along, doing work on the charge. So this is actually non-conservative work, and so we have an EMF. Now at the moment, we're just going to work in magnitude. Eventually, there's going to be a minus sign that shows up in this equation. But for now, we'll just work in magnitude. It turns out that the magnitude of our induced EMF is the time rate of change of the magnetic flux through the loop in question. Now you might say, wait a minute, this sure sounds like you're creating yourself a perpetual motion machine of the first kind, which would violate the first and second laws of thermodynamics. You know, that's a machine that runs forever and does useful work. But keep in mind, we only have these electric field lines for so long as the magnetic field is changing. You can't keep it changing forever. So, and you have to do work in order to change it. So this is not a violation of the second law of thermodynamics. If you have a coil with multiple turns, though, then that means you will do multiple laps. So if you have an N-turn coil, the magnitude of the EMF will be equal to N times d phi b dt. So in a few videos, we will write this in a little different way to make the relationship between the electric and the magnetic fields more explicit. But for now, one way that we can do non-conservative work on charges is if we can make a time-varying magnetic flux. So let's just try a quick example of that. Let's say you have yourself 1,000 turn coil, and no, I'm not going to draw all 1,000 turns. And let's say we have a magnetic field going through the coil like so. It is initially 0.1 Teslas, 0.1 Teslas, and it'll drop to 0 Teslas in 10 milliseconds. Let's also say that the diameter of our coil here, D, is 2 centimeters. So during the time that the magnetic field is changing, we will induce an EMF in the coils. And so what we want to know is, how big is that EMF? Okay, so by Faraday's law of induction, this will be equal, the magnitude of the EMF, which is all we can solve for at the moment, will be the number of turns times the time rate of change of the magnetic flux. Now here since in the absence of other information, we're going to have to assume that this change occurred uniformly, so that means the D's can turn into deltas. So this will be N times the change in B times A, And here our area vectors will be pointed along the magnetic field. So we'll have a cosine of 0 degrees, or if you prefer 180, but it doesn't matter, we're taking the absolute value anyway. So that'll become 1 over delta t. Now the area isn't changing with time, so we can pull it out, and the area of a circle is pi d squared over 4. So we're just left with the time rate of change of the magnetic field strength. So let's go ahead and put it in. So we have 1,000 turns, pi, now we said 2 centimeters, so I'll have to put in 0.02 meters squared over 4. And my final magnetic field strength was 0 teslas. My initial was 0.1. And we said this was over 10 milliseconds, so 0.01 seconds. You'll actually get a flurry of cancellation here, and you just get pi, just because I was being extra like that. Now let's take a look at the units here. You have Tesla meters squared per amp. I am going to leave that as an exercise for you to convince yourself that Tesla meter squared per second. Tesla meter squared per second. I'm going to leave that as an exercise for you to convince yourself that that is a volt. So it turns out that is pi volts. Now, on a related thought here, want to tie up some more loose ends. Remember, I've been making this illusion that it appears that Faraday's law of induction and motional EMF amounts to the same difference. And like I say, it does under the hood, although proving that is not obvious. So now let's go back to our case of our rails with the bar going down it. If I make this resistance equal to infinity, and we say that the separation between the rails here is L, this is literally no different than my airplane wing. So the airplane wing didn't have any way for current to flow, and so if I stick an infinite resistor here, this is what physicists call the equivalent problem. Electrically, it's the same difference as the airplane wing we were looking at when we were looking at motional EMF. All right, so let's go ahead and put in our magnetic field. There we go. And we're going to need one more dimension here, since in order to do Faraday's law, we're going to need an area. So let's go and dimension this distance right here as x. All right. So by Faraday's law of induction, the motional EMF will be equal to d phi b dt. And here, since we're saying the magnetic field is uniform and the area is increasing, the rate of change of flux is positive. So here we can just get away with dropping our absolute value signs if we're just solving for the magnitude of the EMF. All right, so this will be d dt of b times a times the cosine of the angle between b and a. Well, again, this is either 0 or 180, but we took some absolute value action here. So this is going to work out to be 1 either way. And here, the magnetic field strength is a constant, so I can pull that out of the derivative. I'm left with dA dt. But dA dt is going to be d dt of L times x. But the length is a constant, so of my airplane wing, so I can pull that out. So it's BL dx dt. Oh my gosh. The induced EMF is BLV via Faraday's law of induction, which is exactly the same result we got before when we considered magnetic forces. And this turns out to always be the case. In physics, because nature needs to be internally consistent, if we have two different ways to get to the same answer, it jolly well better always give the same answer in all cases. If not, if it breaks in even one little aspect, then that means we have to go back to the drawing board because something about our model is incorrect. But here it has been proven that this is all the same under the hood, although it is pretty subtle to do that and beyond the scope of this treatment. All right, so to finish out this video, I want you to go ahead and take a look at this demo here. So today we're getting a return visit from our friend, the ridiculously powerful magnet. Now what I also have here is an absolutely ordinary copper pipe, the kind you can buy from any big box store. Now copper is not magnetic. We can see here it doesn't want to stick. In fact, I can even just drop it nearby. We see it falls normally. Nothing special there. Now what I'm going to do is I'm going to drop the ridiculously powerful magnet through the copper pipe. I want you to predict what's going to happen there. So go ahead and pause the video and make your prediction. Okay, do we all have our predictions here? Let's see what happens. Well, sure looks like it took an awful long time to fall. So what's going on with that? All right, so what the heck do you think is going on here? Pause the video for a bit and see if you can come up with an explanation for what you just saw. All right, so the name of this phenomenon is eddy currents. Now when I dropped the magnet through the copper pipe, I don't know if it was the north end down or the south end down. It turns out not to matter. It will just basically turn the whole diagram upside down, but the result will be the same. So we'll say this is the north end here, that's the south end there. And if the magnet were the other way around, like I say, just, I don't know, do a headstand and look at the monitor that way if you prefer. But the result will be the same either way. So let's just draw a few magnetic field lines here and here. All right, so they'll be doing something like this. All right, so now if I am, the way to think about this is think about like little washers, you know, like little thin rings of the copper pipe immediately above and below our falling magnet. And actually, let's go ahead and just note that the magnet is indeed falling down. Alrighty. So if I look at a little bit of washer or of copper ring underneath here, so I'm imagining sectioning this copper pipe into a whole bunch of rings. Let's look at this ring right here. As the magnet falls down and it approaches this ring, is the flux through this ring going to go up, go down, or stay the same? Pause and get back with me. So yeah, it's going to go up. So we're going to have an increasing downward flux, which means that we will have to have an upward pointing induced magnetic field, which means that we will have to induce a current in this ring of pipe going like this. And of course, looping back around on the back side. Alrighty, now let's go and take a look at a corresponding ring of pipe above. Is the flux through this chunk of ring here going up, down, or staying the same? Pause and get back with me. Right, here it's going down because as the magnet falls down, more and more the field lines are missing the loop. So we want to reinforce the collapsing magnetic field. So for any of the rings above, we're going to induce a magnetic field pointing down, which means that we will have currents flowing the other way around at the top of the pipe. Okay, but if we think about it, these induced magnetic fields that these currents are making are themselves basically acting like tiny little bar magnets, right? So right here, this would correspond to a north end, and this to the south end of the magnet created by this ring. And here, this would be the north end, and that would be the south end. So here, I got a north next to a south. It's trying to attract the magnet up. And here I have a north next to a north. It's trying to repel the magnet up. In both cases, we end up exerting on the magnet a magnetic force pointing up to counter against our force of gravity down. And in fact, because of how ridiculously strong the magnetic field of this particular magnet was, we pretty much just hit terminal velocity almost immediately and fell through the pipe at a constant speed. Alrighty, so in the next series of videos here, we're going to be taking a look, starting to take a look at electronic devices called inductors and transformers that work off of Faraday's law of induction. Catch you over there.